Hey everyone, in today's lesson we are learning about another measure of spread called the standard deviation. So let's get started. So on our last lesson we looked at the interquartile range, which was a measure of spread that uses the median as its central value. And so today we're looking at a measure of spread that uses the mean as its central value, and it's called the standard deviation. And this will be very important for our next unit on continuous probability distributions. So to start, I've given you guys a set of values, and we're going to investigate how spread out the data values are by finding how far each value is from the mean. These distances or differences are called deviations. So a deviation can be positive if a value is above the mean, or negative if it's below, or zero if it's right on the mean. So let's look into this. So first of all, to know how far these are from the mean, you need to know what the mean is. So there's 7 values here. Finding the mean will be very quick for us. So let's just quickly do that. I think I've cooked this up, so it gives you a whole number. Yeah, 7 values. Yeah, so the mean is 51. And I've assumed this was a sample, so we've used X bar for estimate for the mean. So to get the deviation, you take the data value, X, and take away the mean. So I'll write out this calculation for the first one, but you don't need to write this calculation out in practice. You can just hammer it out. So 50 minus 51 is -1. So the deviation for the value of 50 is -1 because it's 1 below the mean. 48 is 3 below the mean, so -3. 55 is 4 above the mean, so 4. 44 is 7 below. 45 is 6 below. 51 is 5 above. 59 is 8 above. So those are all the deviations. We found how far each value is from the mean. I want you guys to investigate. What is the average deviation? Maybe that will tell us something useful, like how spread the data is. Are all the values are they in general far from the mean, close to the mean? Well, let's find the average deviation and find out. So if you want to pause the video, add those deviations to find the average, you can do that. Or you can follow along with me. So if we add these guys up, I think I can do this mentally. -1, -3 is -4, plus 4 is 0. Then I get -13 plus 13. The total is actually 0. So if you average, well, so the total is 0. So the average deviation would be 0 too. And that's not very helpful to us. It actually makes sense that these deviations add to 0, because that's kind of the idea behind the mean. It's kind of like the central value for all these data, some above, some below. So it makes sense when you add them, you get 0. But this average deviation won't help us. So instead, we have some other measures of spread we calculate. So we calculate something called the variance. So instead of finding the average difference or average deviation, we find the average of the squared difference or squared deviation. Because let me flip back for a second. If I were to square all these numbers, then they would all be positive. And then it would make sense to find an average. I'd get something meaningful. But right now, they're just all, no matter what the data values, the data set is, the average deviation will always be 0. So we don't find the average deviation. We find the variance, the average of the squares. So here, there's a lot of formulas and notations. Let's actually talk about this. So first of all, let's look at population variance. So you can see the formula is actually makes a lot of sense. It's an average. That's what sum means, right? Sum means total. And x minus mu, well, mu is just the mean, right? So these are all the deviations, but they're squared. Deviations squared. So you square all the deviations, you add them up, and you divide by the population size, so the total number of values. So it's actually an intuitive formula. Just instead of averaging the deviations, you square them and average that. That's called the variance. Now, the symbol we use for variance will sink in and make a bit more sense after we learn our next measure of spread, the standard deviation. But this is the Greek letter sigma. And the symbol that we use for variance is sigma squared. Now, that's the formula we use for a population. If we have all the data values in our population, if we only have a sample, we use a modified formula. So we use S squared for sample variance. We still average the deviations, right? Mu and X bar were just two different symbols for mean that we use when we have population versus sample. But when we're calculating a sample variance, we divide by n minus 1 on the bottom. The sample size minus 1. So this gives us a little bit more something more meaningful. And kind of the meat and potatoes of today, the kind of where we're getting to is this, the standard deviation. If you square root the variance, that's what the standard deviation is, what you get is the average distance of data values from the mean. So we square the deviations, we average those squares, and then when we square root to undo that squaring, what we get is an average distance or an average deviation from the mean. And the formulas for this standard deviation from the mean it's just the square root of the variance. So the standard deviation symbol we use is this, again, it's this Greek letter sigma. And the formula is literally just square rooting our formula for variance. And for sample standard deviation, we just square root the sample variance. Now, you may be wondering why the difference. Why do we use n for the first one, it's a population, and n minus 1 for the sample? So the idea is, and this is teasing a little bit into our next unit, but if I was measuring something like, the average mass of like newborn babies, what you're going to get is you're going to get an average or a mean. I'll call that mu. And you'll have a lot of values close to, some below, some above. And then you'll have your outliers that are far away. Now, what happens is when you're doing a sample, what happens when you do a sample is you're more than likely you're getting sample values that are close to the mean. You don't get a lot of the outliers. And because you don't get a lot of the outliers, the measures of spread you get for your sample, without the outliers make the measure of spread very large. But if you don't have those guys, then the measure of spread looks small. In the sample, standard deviation is smaller than it should be. So to compensate for this, we divide by a slightly lower number. So instead of dividing by n, we divide the samples by n minus 1, and that kind of compensates and gives us better estimates. The math behind proving that is something for if you're taking some university level statistics courses. I didn't see it till my third year of university. So that's the difference. Now, these formulas will always be given to you, but hopefully you work with them enough that they just become second nature to use. So now that we've talked about variance, standard deviation, let's go back to our example and calculate the sample variance and sample standard deviation. So let's go back to here. Now we're going to make use of this last column. If I could find the pen I use for. So you guys, there it is. We're going to add a column here at the end. We're going to square all these deviations. So x minus x bar squared. In practice, you won't always have a table like this. You might even like to create one of your own. And a lot of times you'll just use technology to calculate variance standard deviation as well. but adding this column can be helpful. So we're going to square all our deviations. So remember, when you square a number, you're going to get something positive. Or you could square 0 and get 0, but you're no negatives in this column when we're squaring. And these are all whole numbers, so we can just use mental math here. 49, 36. So you can see those values that are really far from the mean really have an effect on the variance and standard deviation, because when you square them, they get that much bigger. And 64. So now we can add these up. So 10 plus 16 plus 49 plus 36 plus 25 plus 64. So that gives us a total of an even 200 for the sum of the deviations squared. So let's do the sample variance, S squared. That is the sum of all the squares of the deviations divided by the number of data values minus 1. We've actually already done the top. This is what this last column did. It got all the deviations, squared them, and we already totaled them up. That value we got was exactly 200. So that just goes right in the top. And we had 7 values. Subtract 1. So we're doing 200 divided by 6. So you get, 100 over 3 if you want to be exact. Or if we just go to one decimal place, about 33.3. The sample standard deviation is just the root of the sample variance. So I'm writing a lot down here, but all we had to really do is root 100 over 3, or root 33.3. And when we do that, we get about 5.77 for our sample standard deviation. So what this means is that we could say, so the mean of this value, this data set is 51. And we can now say a typical value is about 5.77 units away from the mean. So we now have a way to describe how far a typical value is from the mean. A standard value, a standard deviation. That's where the name comes from. All right. Why don't we get you guys to try it? So here is a set of 8 values. I've asked you to find and I've said it's a population. I'm going to have you guys try finding the variance and standard deviation for this population. So you'll need the mean. You can use the table if you'd like. So you're going to find the deviations, x minus mu, and then you're going to square them. So you can pause the video and try that, or you can just kind of work along with me. Now, I believe when I cooked this up, I designed it so that you get not a whole number, but at least a decimal that terminates. That'll make finding our deviations easier. Yeah, divided by 8. So the mean I got for our population mean, I got 10.4. So that makes our deviations easy to calculate. Negative 0.3. I got to be careful here. Positive 0.8. 9.4 is 1 below the mean. 10.1. Negative 0.3. 10.5 is 0.1. 12.5 is 2.1. 8.7. I think it's 1.7, but it's too early in the morning to risk getting that wrong. 1.7 and 10.7 would be 0.3. Now, when you're doing this by hand, I know we already did an example where we added the deviations and got 0. That's just actually a good thing to do in practice as a bit of a check to make sure you did your mean correctly and all your deviations correctly. So I just do that all the time. So I'm just going to add up all my deviations and then just make sure I get 0. That is negative 1.7. Yeah, they added a 0 for me. So I know I'm good. So now I can go on and find all the deviations squared. So that's 0.09, 0.64, negative 1 squared is 1, 0.09, 0.01, 2.1 squared, probably should know that, but 4.41. I think this is 2.89, but yeah, 2.89. And 0.09.3 squared. All right, so ready to go. Let's get the total. We're going to need it. 0.09 plus 0.64 plus 1.09 plus 4.42 plus 2.89 plus 0.09 equals 9.22. So that's the sum of all our deviations squared. So now we're basically done. We've done all the legwork, right? So to find the variance, sigma squared, we add up all the squares of the deviations, and for a population variance, we divide by the population size. And we did that top, that's 9.22 we got, divided by 8 values. So the variance, 9.22 divided by 8, about 1.15. And our standard deviation, our population standard deviation, is just the square root of the variance. The square root of about 1.15, about 1.07. So we can say here that sorry, but you can just hear my kids. You can say that a typical value here is about 1.07 units from the mean. All right, at this point, I want to show you guys the functions in Google Sheets that can help you do this using technology, because you don't always want to do this by hand. So here we go. All right, my wife just closed the door, so it should be better. All right, I've got the same values I used in our last lesson, actually. I'm going to show you guys the formulas for all these 5 things. So to get a mean, so the mean is like average. So you can just use average. There's a function for that in Google Sheets. Average, highlight what you want to do. 7.25 for this data set. You don't need to actually find the average to use a spreadsheet program to find the variance or standard deviation. So in Google Sheets, if you want to do the variance for a sample, so use VAR for variance, and you'll see there's 2 things. There's variance of a sample, and there's variance of an entire population. And there's also various other ones. I just use this one, variance of a sample and variance of a population. So sample variance, and let's compare the population variance. So you can see they give values that are not terribly far apart, but if you remember, for the population standard deviation, you're dividing by n, and for sample, n minus 1. So if you're dividing by a smaller number, you're going to get a bigger sample variance. So you can see here, it's a little bit bigger than if you're just dividing by n. And for the sample standard deviation, so you have the features, so STDEV, standard deviation. You have I like using these 2. So standard deviation of a sample versus an entire population. So for sample, and you notice that this just gives you the result as if you square rooted the variance. And for a population, use the P. So I make a mention of this later on when it's time to do some practice, but make sure you can do them by hand. You know the principles behind how a standard deviation is calculated. But if you're doing practice problems and you need a standard deviation to do some other thing, then just use technology, right? And I've shown you how to do that. So keep that in mind. Make sure you can do things by hand, but also know how. Also, feel free to use technology too. Right. This just brings us to our next topic, which is Z-score. So Z-score indicates how many standard deviations a value lies from the mean. So you can calculate Z-scores using this kind of intuitive formula. So to find out how many standard deviations a value is from the mean, you find its distance from the mean. We've called that deviation. So either x minus mean or x minus x bar. And then you divide by the number of standard deviate, or you divide by the standard deviation. And that gives you how many standard deviations you are above or below the mean. And this is going to be really useful for our next unit too. So again, these formulas will be given to you, or you'll have them at home. But it's really intuitive. You take the deviation and you divide by the standard deviation. And that tells you how far that value is from the mean in terms of how many standard deviations. All right. We are going to, I think on your sheet, I asked you guys to find some Z-scores. So I'm going to do that with you here. Use yellow so it shows up better. So we're going to go to our previous example, and we're going to find a Z-score for, I think the first one I give you guys is 9.4. I think I said that's our third data value was 9.4. And this was a population. So the Z-score for this one, so to get a Z-score, you take the value, which is 9.4. You subtract the mean, which in our case we got was 10.4, I think. Yep, 10.4. So 9.4 minus 10.4, and you divide by the standard deviation, which we got as 1.07. So that's -1 divided by 1.07. So we get about -0.93. So this means 9.4 is 0.93 standard deviations below the mean. Now, for the next one, I believe I have x5 being 10.4. Now, I know that's not what it is in the table. In the table, our fifth data value was 10.5. Last minute, I was like, well, I want to actually show you guys what happens if a data value is on the mean. What happens with our formula? So just humor me. Let's just imagine a data value in that set was 10.4. What would the Z-score for this one be? Well, we would take 10.4 and we would subtract the mean of 10.4 and divide by the standard deviation, 1.07. But that's a 0 on top. So a data value of 10.4 would have a Z-score of 0 because it's on the mean, which that makes sense. If it's on the mean, it's no standard deviations from the mean. It's on the mean. And for our last one, we're going to look at X6, which I think was 12.4, but I'm just going to flip back and double check. 12.5. The Z-score for that guy, you take the data value, you subtract the mean, 10.4, divided by 1.07. So this is 2.1 divided by 1.07. So this value is almost 2 standard deviations above the mean. And this idea of Z-scores is going to be really useful for us in our next unit when we talk about something called a normal distribution. But so far, given a data set, you guys should be able to find a variance or standard deviation, whether a sample or a population, and you guys should be able to find a Z-score. You should be able to calculate how many standard deviations a value is from the mean. And it's just a matter of using this formula. But Z-scores can be negative if the value is below. Z-scores can be 0 if the data value is the same as the mean, or they can be positive if it's above the mean. All right. So what's really cool is that there is other equivalent formulas for standard deviations that don't actually require you to find the deviations and square them. It can be shown, and we're not going to do this. It's a little bit above the scope of this course, but these formulas give you the exact same standard deviations. For a population, this notation here says you square the data values and find the sum of those squares. Then you take away the population size times the square of the mean and divide by the population size, you get standard deviation. For the sample, it's the same thing, but you divide by n-1 like we're used to. So let's verify this works with our first example. So we'll switch back to black here. So for our first example, the mean was 51. And just going to be paranoid right now and just actually check that out. Yeah, it's 51. And the reason these formulas, you may like them or prefer them, because if you're doing things by hand, all you need to do is square the data values. You don't need to do, just saves you a bit of work. Now, these numbers will be a bit bigger. So if you want to do this along with me here, we just need to find all these squares. Yeah, it can save you some work. 55. So what we're hoping to see here is we're hoping to get the exact same value that we calculated earlier on. And we're way too far into the video lesson for me to stop and redo it. So I really hope this works out. I'm sure it will. 2025, 56 squared, 3,136, 59 squared, 3,041. And then we just have to total these up, and then kind of the heavy lifting is done. Plus 2304, plus 3,025, plus 1936, plus 2025, plus 3136, plus 3481 equals. I got 18,407. So I guess we'll find out if I'm right later on. So let's find the sample standard deviation. We're going to be doing the square root of. So our new formula says, I'll just write it out actually. We're going to find the sum of the data values squared. We're going to take away and this was a sample, so I'll use little n times the square of the mean. Then we'll divide by n-1. So on the top, the sum of the squares of all the data values, we did that. It's 18,407. There are 7 values here, and we're multiplying by our mean squared. And we're going to be dividing by 7 minus 1, the same as before. So what we're hoping to see is when we do this calculation on top, we get what we got earlier on. We did the same problem. And whoops, didn't mean to do that. It's okay. But we get the same value. We get 200. If you recall, for the standard deviation from before, we got the root of 100 over 3. It's the exact same thing. That's pretty cool. We did it. So we got about 5.77. Of course, it'd be unreasonable for me to ask you guys to memorize these formulas, the alternate version of standard deviation. But it would be reasonable for me to say, here's this data set, try find the standard deviation using one or the other, or both, which is like this next one. So this next one, only 5 values. We're going to find the population of standard deviation. And try using both formulas, and it should give you the same value either way. So I've given you guys an extra column there to have this squared, as well as to do your work with deviations. So give it a go if you want to pause the video, or if you also want to follow along with me, that's fine too. 14 squared, I think is 196, yep. 121, 18 squared, 324, And 16 squared is 256. When I total those guys up, 196 plus 121 plus 324 plus 256, get about 906. So let's actually use this version right away. Let's see what we got. So we've done the sum of the data values squared. We got 906. You're going to subtract 5 times the square of the mean. So let's just get the mean off to the side here. This is the mean of the data values, 13 plus 14 plus 11 plus 18 plus 16 divided by 5, 14.4. And divide by the population size, and then square root it all. So most of you guys could probably handle this in one step on your calculators. For the top, I got 834 divided by 5 and square root. About 12.9. Say 12.92. So I'm expecting to get the same result if I use the other formula. And so let's try that out. So our mean was 14.4. 13 is 1.4 below that. 14 is 0.4 below that. 11 is 3.4 below that. 18 is 3.6 above. 16 is 1.6 above. And I'm going to do that quick mental check here. Can I do mentally? Yes, I can. And those do add to 0. Checks out. So I'm going to square these guys. So I get 1.96, 0.16, don't know 34 squared, 11.56, 3.6 squared, 12.96, and then it'll be 2.56. Let's add these up. 1.96 plus 0.16 plus 11.56 plus 12.96 plus 2.56. Keep in mind, hopefully none of you guys got caught on this. When you square a number, you always get a positive or 0, but you shouldn't have any negatives in this last column here. So I got 29.2 is the sum of those deviations squared. So for the this, we got 29.2. Let's just finish this off because I think I see a mistake I made in the first one. 29.2 on top, divided by 5. And let's finish this off. Divided by 5 equals, and then shift root equals 2.42. So let's see what we did wrong with the first one. Oh, the mean squared. I didn't square the mean here. Okay, good. So hopefully you at home noticed that and you didn't have a panic attack. You just kind of followed along, hoping that I would catch my mistake. And I did eventually. 14.4 squared. 906 minus 5 times 14.4 squared equals. Okay, did I square these right? This isn't checking out. 169. 13 squared. 14 squared. 11 squared, I know that. 18 squared, 324. 16 squared, 256. 169 plus 196 plus 121 plus 324 plus 256. I think it should be bigger than 906. It is bigger. Oh my goodness. Well, we caught it. It's 1,066. 1,066. And now maybe this will work. 5 times 14.4 squared equals, yeah, all right. 2.42. So actually in hindsight, and this is something that you guys should do too, when I got a standard deviation of 12.92, I should have looked back at my data values and say, there's no way that a typical value here is 12.92 units away from the mean. So I should have caught that earlier. and should have said, hey, something's up here. If that's math for you, it's definitely okay to make mistakes. Good little learning moment there. But yeah, each formula should work if you don't make 2 mistakes like I did. All right, so as I mentioned earlier, try a few by hand, but I know it's a bit of a grind doing standard deviation and variance by hand. So just do a few. Make sure you can, and then if you want to, just make sure you can use Google Sheets or Excel or whatever spreadsheet program you use. Make sure you know how to calculate a Z-score. But yeah, don't feel like you need to crank out all these by hand because I know it's a bit of a grind. So using your text or the handout, the PDF I have posted on the on Brightspace, here's some questions for you to try. That's really it for content for our one variable stats unit. We'll spend a couple days talking about statistical summaries and maybe have a little bit of a task for you guys. But yeah, that really wraps things up. So give the practice a try. Hope you guys have a great day, and we'll see you soon.